Okay, so this was the last example we had done, which was talking about how to find the intercepts and graph our function. Obviously, we had seen that intercepts themselves were not enough, so we had to find a few more points, and I believe we had done a table for number 9. So just immediately after example 9, you'll see that we're talking about how you can also use the quadratic formula to help you find these x-intercepts. And of course, additionally, we know that the x-intercepts, if you have both of them on your graph, should be on opposite sides and of course the same distance from the axis of symmetry. So when in doubt, if nothing else works, remember you can always use the quadratic formula to help you out with finding the x-intercepts. So kind of building up on what we had done with the graphing, we're getting into quadratic inequalities next. So with quadratic inequalities, we're actually going to look at this with two different methods. One of them is going to be the graphical method, which is what we're doing next, and then we'll also try and do a test point method, which may actually be a little bit more effective than the graphical one. So anytime we're talking about an inequality, of course, we know you are looking at the greater than, less than, greater than, equal to, less than, equal to symbol. When we're talking about quadratic inequality, of course, we're talking about a quadratic function being part of that. So I think it was chapter 1 where we had talked about linear inequality. So in this section, we're talking about quadratic. So notice how your inequality will be of the form ax squared plus bx plus c, and you can think of that as being your function y equals that value. Now, when you are trying to solve the inequality, the idea is we're actually still trying to find the x values that would satisfy our inequality or our function in this case, which also means you're still finding your x-intercepts. They're calling it roots. You can call it zeros. You can call them solutions. All of those terminologies are still talking about the same thing, which is finding your x values, your x-intercepts. So the first thing we're going to do is make sure we get all our terms on one side and 0 on the other side of our inequality. Solve for your roots, so that's finding the x-intercepts. And then we're talking about graphing that corresponding equation. So you can use the x-intercepts for that. Again, anytime you're graphing a polynomial or a quadratic function in this case, you need to have more points to make sure you have enough points to graph that. And then we're actually going to try and use the graph to see what solution set we can get that would satisfy our inequality. So we're starting with our first example here. They're saying solve each inequality, write the solution set in interval notation, and graph it. So that's the first thing we're going to do, is try and get our x-intercepts and then graph this. So the first step here should be to get all the terms on one side, 0 on the other side. So what should I move here in this example? What term can I move? Yeah, you want to move the 8 and bring it to the left-hand side and get 0 on the right-hand side. Right now, we are given x squared minus 2x greater than 8. Start by subtracting that 8 and bringing it onto the left-hand side. We end up getting x squared minus 2x minus 8 greater than 0. Of course, keep the same inequality symbol, right? So this is our function, x squared minus 2x minus 8. So we can call that y, and we can have y equals x squared minus 2x minus 8. And then what can we do to find our x-intercepts? Or the roots, as they're calling it. Remember, that means set it equal to 0. So you have 0 equals x squared minus 2x minus 8. Now this expression, can it be factored? Or do we need to use a quadratic formula? Or what should we do to get our x values? Because if you can factor it, that would be the easiest and the quickest way to do it. If you cannot factor it, then of course you can use the quadratic formula. So think of two numbers that multiply to give you -8 and add up to give you -2. +4, -2?
No, wait, -4, positive.
Yeah, you want to make it -4 and a +2 to get that combination to work, which would end up giving us x minus 4 as one of the factors and x plus 2 as the other one, and then set each one equal to 0. And of course, this guy will give me x equals 4. This guy will give me x equals -2 when you get x by itself and move the numbers to the other side. Okay, so those are our roots. Now, as far as graphing goes, what else do we need? So we've got +4, we've got -2 as our, well, x-intercepts, where the graph will cross the x-axis at. So obviously that's not enough information. At this point, since we have talked about the vertex, we should definitely try and find where the vertex of this parabola is going to be, and also try and find where the y-intercept is going to be. Because more than likely we will have a y-intercept as well. So let's start with the vertex. So if our equation is given as x squared minus 2x minus 8, how do I find the vertex of this parabola? You should be able to look at a couple examples and see how we calculated the vertex when it was given to you in the standard form. Which one was it? Yes, Amy?
It's the negative b over 2a is
Yeah.
first coordinate, and then f of negative b over 2a.
Yeah, then put it back in. Very good. So find your x coordinate by using -b over 2a. In this case, and let me see if I can pull that up. Your a is of course coming from the square term, the b is coming from the middle term, and c is the constant term. So -b over 2a. So looking at our function here, what is b? -2, and what's our a? +1. You're going to end up with negative times negative, which is +2 over 2, which will give you 1. And what will be its corresponding y value, which will be x squared minus 2x minus 8. What does that do?
9.
Yeah, -9. And I guess we'll do the y-intercept calculation here, making our x value 0, which will again basically be y equals x squared minus 2 times x minus 8. So what does the y-intercept come out to be? Yeah, -8. Or the ordered pair, 0, -8. Again, if we wanted to write these guys as ordered pairs, that's 4, 0, -2, 0. So let's see, I think we should have enough information now. So our vertex as an ordered pair will actually be 1, comma, -9. So 1, -9. I think I just made these guys 8 by 8. And then 0, -8 is where your y-intercept is at. So this is our lowest point on the graph, crossing the y-axis, and then crossing the x-intercept. That's kind of what this graph should end up looking like. Okay, so we put our equation in the standard form, which meant bringing all the terms on one side, getting 0 on the other side. Then we found our roots, which was basically finding our x-intercepts. Once we did that, to finish the graph for this parabola, we found the vertex of the parabola because that would tell us what the lowest point is since this parabola opens up. And then we also found our y-intercept, so that gave us enough points to get the general shape of our parabola. Now, how do I use this graph to actually solve our inequality? So if you go back here, you have x squared minus 2x minus 8 is greater than 0, or in other words, y value is greater than 0 since we're representing this as a function. So we want to know for what interval, which means for what x values, will this function give us positive y values, right? And that's not including 0, that's just for the positive y values. So if we go back to our graph, obviously we know as long as my graph is going to be above the x-axis, all of these values are positive y values, which means my graph for this section right here is going to have positive y values. Same thing here. For this section, the graph will have positive y values. Anything below the x-axis will have negative y values, so which means this section here, all your y values are going to be less than 0. Same thing for this guy, they are less than 0. Right at the x-intercepts, we know y is equal to 0. So that means I cannot use this portion of my graph because all the y values are negative. I also cannot include the x-intercepts because that's when my y value is equal to 0. So the only part of the graph that I can use where y values are positive are going to be these little arms, which are above the x-axis. So when you are writing this as an interval notation, remember we are talking in terms of the x-axis. So our solution set is going to be in terms of the x-axis, again, interval notation from -infinity to -2. All the y values for those x values are going to be positive. So anything from -infinity to right here, which is -2, not including -2 because we don't want our y to be equal to 0. Now in that same way, how do I write for the other arm of my graph?
Or I can't think of the name of it.
Parentheses.
Parentheses 4, comma, infinity.
Yeah. Because again, I start at the value of 4 and I can go to the right and all my y values for those x values are also going to be positive, not including the endpoint because right at the endpoint, my y value is going to be 0. And since they are again in two different portions, you use the union symbol to combine them. So as long as your x values are going to be anything from -infinity to -2 and from 4 to infinity, all the y values in this function are going to be positive numbers. And you can try that, right? Just pick a number between -infinity and -2. Plug that x in here, you should get a positive y value. You can try it with something like -3. In that same sense, pick a number from 4 to infinity. So again, you can go with 5. If you put 5 in for your x, you should again get a positive y value. So that's what the graph is doing, is basically showing you where are the y values going to be positive, where they're going to be negative, and then based on the direction of your inequality symbol, you have to pick the interval where the solution set will work. So number 11 is a continuation of this same function, same graph. So the only difference is we are changing the direction of your inequality symbol. So look at number 11 and tell me, what do you think that solution set should be? So they're giving you x squared minus 2x less than equal to 8. Same thing, bring the 8 over to the left-hand side. And then use the same graph to try and see what your interval notation should be. So where is that inequality going to be less than and equal to 0? On what interval? Any?
So it's -2 and 4 with brackets, including.
Yeah, because in between these two numbers, if I use any x value from here between this interval, they are going to be part of this portion of our graph, right? Which means you are going to get a negative y value in there. And of course, you can see this is a good example because 0 is right in the middle of that interval. When I use 0, my y came out to be a negative number. So any number that's going to be between -2 and 4 will give us a negative answer. And right at -2 and 4, we're going to get our 0. And since this is less than or equal to 0, which means you are including your endpoints in this case. So between -2 and 4, including the endpoints. Alrighty, very good. Questions on 10 and 11? Alright, so this is of course our graphing method. And we've kind of talked about this before also. You know, we don't normally try to just depend on graphs to help us out with any kind of an algebraic solution. Normally, we want to make sure that it's going to work every single time. And what happens with the graph is for some functions, we may have a simple enough graph like we looked at in number 10, but sometimes the graph may not show all the important features of your function. So we don't really want to just base these examples on the graphing method. So we're actually going to look at the test point method. And test point method, you're basically bypassing having to draw a graph. A lot of it is going to be similar in process, with the exception of we don't really draw a graph after we find our roots. So you're still going to need to get your 0 on one side, move all the terms on the other side. We're still going to find our roots, which is our x-intercepts, but instead of graphing, we're actually going to put it on a basically a horizontal axis on a number line, which represents our x-axis. That's all we're going to do. Once we have our intervals separated by the roots, from each interval we pick a test point. That's like a representative point for that interval. And we try and see for which interval our function is going to be positive, for which interval is going to be negative. And then depending on where we have a positive or a negative, we can determine what the solution of our function is going to be, or in this case, our inequality. So just to kind of show you what that would look like, let's say if this was the example that we did using the test point method. So with a test point method, we would have still found our roots. So with the test point method, we have our little number line. Our roots were -2 and +4. So from each section, we would have selected a test point. So something which is smaller than -2, we could have picked 3. Between -2 and 4, 0 kind of always seems to work out best. Greater than 4, we could have picked a 5. Now, just by looking at the graph, and since we've already done this example, we know that in the interval from -2 to infinity, which is where I picked this test point 3, all my y values are going to be positive. So I'm actually going to end up getting a positive for that interval. In the middle, between -2 and 4, we know all our y values are negative, so I will actually get a sign of a negative in here, and the last one, greater than 4, again gives us positive sign. So that's what a test point method does, is you draw the number line, put your roots in there, which is the -2 and the 4, pick a test point from each interval, plug those test points basically into your function, right? So 3, 0, 5 would replace our x in the function here, and we would see, do I get positive or negative signs? If my inequality is greater than 0, I'm looking at the positive intervals. If my inequality is less than 0, I'm looking at the negative interval. And of course, if they do equal to, we put brackets on our endpoints. So that's kind of what the idea behind a test point method is. So we're changing our function here. You've got x squared minus 2x minus 4. It's already in the standard form. So we need to start by finding our roots in this case. So for we've got x squared and this time they're giving us less than 0. Now, can I factor x squared minus 2x minus 4 to find our roots? No, because 4 only has 2 sets of factors, 2 times 2 and 4 times 1, and none of them are going to add up to give us -2 in this case, which means to find the roots, I think quadratic formula is going to be our easiest process here. So let's start with that. So that's -b plus or minus the square root of b squared minus 4ac, and the entire thing divided by 2a. Let me see what you guys come up with for your roots for number 12. So what will be our a, b, and c values here? All right, you guys. So our a term is going to be 1, b is -2, c is -4, which will end up giving us negative of -2 plus or minus -2 squared minus 4 times A times C divided by 2 times A. Okay, so just make sure your signs are correct and your numbers are in the right place. In the front, of course, negative times negative will become positive. Inside the radical, negative 2 times negative 2 will become positive 4. And then we are doing negative 4 times 1 times negative 4. So again, negative times negative positive, and 4 times 4 will of course give us the 16, right? And then denominator is just 2 times 1, which will become a 2. Just cleaning the square root part up will give us square root of 24 plus 16. And this is kind of what I was talking to you guys about, of how do we simplify square root of 20. Actually, let's do that part first. So square root of 20, how can I rewrite it where I can bring a radical outside of it or simplify it? 20 can be broken down into 2 times 10 and 4 times 5. So you want to see which one of those has a perfect square. And that's again 4 times 5, because square root of 4 cannot come outside as 2. 5 cannot be broken down anymore, so that'll stay as square root of 5. So we should have at this point 2 plus or minus, we just simplified our square root of 20 into 2 times square root of 5. And then we're dividing everything by 2. So I can see that my first term has a 2, this term here has a 2, and of course my denominator is also a 2. So you can actually factor out a 2 from your numerator. I'm bringing this 2 outside, so I need a placeholder for it, which will become 1 plus or minus. Again, since I'm factoring out a 2, this 2 will also go outside, leaving us behind with just the square root of 5. So the reason I like to factor it out, so that you will remember that this 2 needs to go into the 2 in the front and the 2 with the square root of 5. So factoring actually helps you kind of take care of that. These guys will cancel each other out, leaving us with 1 plus or minus square root of 5. And you know, once you get that value, you can see factoring definitely would not have worked out in this case, because you're getting such an odd looking root for your x-intercepts. Now, if I had to write these guys as ordered pairs, they would be 1 minus square root of 5, 0, and 1 plus square root of 5 and 0. Okay, just to go back to our steps here for a minute. So when we are using the test point method, after you find the roots, you're supposed to plot them on the number line, and then from each interval, select a test point. So what's going to happen here, since our numbers are not quite evident what the value of those is, we're actually going to need to find what their decimal approximations are, so that we can put them on the number line and figure out what our test points are going to be. So let's start with our number line. I know the value of 1 minus square root of 5 is going to be smaller. 1 plus square root of 5 is going to be larger. But to be able to pick these test points, we need to know what are the approximations. So 1 minus square root of 5 is approximately what value? Negative 1.24. And 1 plus 3.24. So remember, these approximations are just to help us figure out where our test points are going to be. These are not our actual roots. We have to leave them in the radical form for the actual roots. So pick a number smaller than negative 1.24, what can I go for?
-2.
Yeah, pick -2 as your test point. Between these two, between -1 and +3, yeah, I normally like to go for 0 because 0 makes calculations a little bit easier. Larger than 3.24. Sorry? 4? Yeah. Okay. Now, we need to test and see what they are going to be in our equation. So remember, our equation is x squared minus 2x minus 4. So we need to check and see, am I going to get a positive or a negative value when I put these test points in? So with our test points, let's start with x equals -2. So that's going to be -2 squared minus 2 times -2 minus 4. What will I get? 4, +4, +4, -4. Looks like +4, right? So +4 means in this interval, all my y values are going to be positive. Okay, so that's the part that will go up if we were trying to graph this. Okay. Now let's try the second test point, which is x equals 0. So that will be 0 squared minus 2 times 0 minus 4. And what will that give us? -4. Yeah, -4. So that means in the center interval, all my y values are going to be negative. And our last test point was +4. So that will be 4 squared minus 2 times 4 minus 4. So that'll be 16 minus 8 minus 4. 4. You still end up getting a +4. And that means in this last interval, everything is going to be positive. So now that we know where our y values are going to be positive and negative at, looking at the original inequality, what will be our solution set? Where is our interval giving us y values being less than 0? So what do we think?
From -1.24 to 3.24.
So you want to use the radical terms, but yeah, it's going to be in between our x values, right? Between 1 minus square root of 5 and 1 plus square root of 5. Am I including my endpoints here with this inequality? No, you're not, because it's just a strictly less than inequality. So you're only going between 1 minus square root of 5 and 1 plus square root of 5. So we're just looking at all these x values between our two roots where our graph is going to be negative. If you had to do just a basic rough sketch for this graph, this is what your graph would end up looking like. We're crossing at 1 minus square root of 5 and 1 plus. So this is the part where our graph falls below the x-axis, and that's why all the y values are negative there. Now, even though this was not given to us, but let's just see what happens if we were to reverse our inequality symbol for the same examples. You've got x squared minus 2x minus 4, and if we did just greater than 0, how would that interval notation change? Bless you. So if we change the direction of our inequality, what would our new solution set be?
-infinity to 1 minus square root 5, and then
Union.
symbol 1 1 plus square root 5 infinity.
Yeah, so kind of what we did in the previous example, because again, from negative infinity to this endpoint, all my y values are positive, and then from 1 plus square root of 5 to positive infinity, all my y values are positive here. And again, you'll notice I kept it as a strictly greater than inequality, which means our solution set for this one does not include our endpoint. So from negative infinity to 1 minus square root of 5, not including it, and then union from 1 plus square root of 5 to positive infinity. Okay. If we put the little equal to sign on that, change the brackets on the endpoints. Obviously, infinity and negative infinity will still never take brackets. It's just going to be on the other numbers. Questions on 12 here? Okay, so you've seen the graphical method with 10 and 11, and you've seen the test point method. And as I mentioned, a lot of times we want to use the test point method because we know that's a more concrete solution, because again, it's not always a good idea to use just the graph to help you out with finding a solution. Okay, so again, in our last class, we had talked about finding the maximum and the minimum value of our function. And remember, that always coincides with the y coordinate from our vertex. So just to talk about applications based on that concept, if you're ever trying to, if you're running some kind of a company, a production house, and you're trying to minimize your cost, that would be an application for finding the maximum or the minimum value of a parabola. If you're trying to maximize profit, same thing. If you're trying to maximize area. So we're saying if one variable is a quadratic function of another, which means you can write one of the variables as a square term, then the maximum or minimum value of the dependent variable will occur at the vertex of the parabola. So our goal in this example here is to, of course, come up with our quadratic equation. And once we have our quadratic equation, try and find the vertex of that equation so we can find where our maximum or minimum value is. And of course, that will depend on, is our parabola opening up or is it opening down, right? Which is what gives you the maximum or the minimum value. So here we're talking about Chandra wants to enclose a rectangular garden with 200 yards of fencing. And we want to know what the dimensions of the garden should be so that she can get the maximum area from this garden of hers. So we know it's a rectangular garden. We know she has 200 yards of fencing. So where can we start so that we can come up with our formula, basically, or an equation in this case? So we have a rectangular garden. And we know there's 200 yards of fencing, which tells us what in terms of a rectangle?
The length is, I don't know how to say it. It's like length plus width is equal to 200. So would that be
And 200 represents what?
the perimeter?
The perimeter, right? So you're talking in terms of fencing, which is going to go around that garden, right? So that's your perimeter. So 200 yards represents the perimeter of our rectangle garden, or just the shape of a rectangle. And as Trey mentioned, you add your two lengths with the two widths, right? So twice the length plus twice the width. We know we have 200 yards of fencing, which means our perimeter cannot be larger than the amount of fence she's already got. So what I'm actually going to do is try and clean this equation up a little bit. Since again, both of these are 2 times the length and 2 times the width, I'm going to factor out that common 2, which will leave us with L plus W inside the parentheses. Divide both sides by 2. And of course, we end up getting, if I just add one length with one width, it should add up to half of that, which should be 100 yards. Now, you either need to get L by itself or W by itself. It really doesn't matter because it's going to work out in either direction. So which variable am I subtracting? Length or the width? Which one do you prefer? Give me a variable, Trevor.
The length.
Okay. So let's subtract the length, which will end up giving us 100 minus L equals W, and we'll come back to him in a minute. Okay. Now, what's the ultimate goal of this question? What are they asking us to find?
Yeah, maximum. The maximum area.
The maximum area, right? They want us to know how we can come up with the maximum area. So what dimensions should we have as far as the length and the width go for this garden? So what is the basic area formula for a rectangle?
Length squared plus width. Wait, no.
Nope.
Length times width.
Length times width, yeah. So the area of a rectangle is length times width, and you will notice we are defining width in terms of the length here. So we're actually going to take this formula and substitute it in the area formula so that I can have, instead of both letters, I'm only working with one letter, right? I'm only working with one variable. So it's going to be length times, and then instead of W, I'm going to substitute it with 100 minus L. You can see this is where our quadratic format is actually going to show up when I distribute that L inside the parentheses. So we end up getting 100 L minus length times length is length squared. So there's 2 things you should notice here. One, we now have a quadratic equation, right? Because my variable L is a squared variable now, so that's my quadratic form. Secondly, my coefficient on L squared is a -1. Remember, whenever you have a negative value for A, our parabola is going to be opening downwards, which means I have a maximum value. So that's what's exactly happening here. So now we need to basically find the vertex of this parabola. So that's going to be our next step, is finding the vertex. And since we have L as our variable, it's going to be L equals, and it's the same formula that Amy had talked about earlier, which is -b over 2a. Same exact vertex formula when your equation is given to you in the standard form. What is our B term for this equation? 100. Very good. And A? Yeah, because that comes from the square term, so A is going to be -1. So that's -b. B is 100, and then 2 times A is -1. -100 divided by -2. Yeah. So our length is actually going to be 50 yards. To find the width, we can actually come back to this formula and find the width in itself. So width is 100 minus L. And of course, you guys should be able to do this calculation pretty quickly. My length is going to be 50 yards and width is going to be 50 yards. So what shape of a garden gives us the maximum area?
A square.
A square, yeah. So she is actually going to need a square garden if she needs to get the maximum area for whatever she's doing in her garden. I don't know if she's growing summer vegetables or I don't know, having dogs running around and she wants the maximum area so they have enough space to run around. It doesn't matter. But the idea is how do you get a maximum area? So you actually have to get a square shape if you're going to get the most out of it. A rectangle is not going to give you a maximum area because even if we know length plus width should add up to 100, right? So you can try different combinations. You can do 49 for the width, 51 for the length. When I multiply 49 with 51, what do I get?
2,499.
2,499. When I multiply 50 with 50? 2,500, right? So you're not by much, but you're still a little bit shy of getting the maximum area, right? With 49 by 51 as your dimension. So yeah, which was a very interesting discovery when I had first selected this example because I would have never thought, oh, let's make it into a square shape if I'm going to get the maximum area. I just kept thinking more length will give you the maximum area, but you know, obviously this proves that a rectangular shape will not maintain that. So any questions on number 13? Okay, so remember we started out with the perimeter formula because they told us how much fencing we had, which was 200 yards. So we basically broke down the perimeter formula where I got one variable isolated by itself, which was in this case getting the, I think we did the width by itself and moved the length to the other side. Once I came up with this formula, we knew we needed to maximize our area, which means we needed to fall back on the area formula, length times width. Since I'm keeping my variable in terms of L, we left the length as it is and we substituted for the width with the 100 minus L. Distribute that L. Your quadratic equation came out to be A equals 100 times L minus L squared. Put it into the vertex formula because you are finding the vertex here whenever they're talking about maximizing or minimizing. Went through that math. Our length came out to be 50 yards. Putting it back into this equation, the width came out to be 50 yards as well. Now, there's a different version of this problem on my MATLAB where I think one side is blocked by like a wall or a barn or something like that. So you're actually only working on 3 sides. So try that example. If you have any questions, let me know and we can definitely look at it, but I'd like you guys to try that example on your own and see how you can kind of use this example but change it up a little bit. Okay guys, so that is the end for 3.1.